Hello and welcome. In this video, we're going to talk about the gradient boosting algorithm. Gradient boosting, again, just like adaptive boosting, tries to boost the performance of weak learners. But the approach taken by gradient boosting is quite different from adaptive boosting. The term gradient in general means slope. And which slope? We want to be taking such direction while updating our predictions, which lead to the minimum loss. That's why the term gradient boosting. Let's get started with some data. So we've taken a small portion of the earlier data that we discussed. We have these columns. There is a serial number which just captures the number assigned to each record. Then we have a credit score. Then we have the average account balance, which is a value in thousands of dollars. And then we have work experience of the individual. And finally, we have the target column or the variable that we are predicting, which is whether the loan was approved or not. When it is a 1, it's an approved loan. When it is a 0, the loan was declined or rejected. So let's say, how does gradient boosting start? It first starts by doing a baseline prediction. In order to achieve the baseline prediction, which will be a probability value, it relies on the log odds ratio. Log odds ratio is a ratio of something happening to not happening, and then you take a log of it. So in our case, if you see out of 5 observations, 3 times we have approved a loan. So if we look at the probability of this, it will be 3 by 5. And if you look at the probability of zeros when the loan application was rejected, it will be 2 by 5. So if we take a ratio of these, we'll get log of 3 by 2. And we've taken log to the base e, which computes to 0.41. Now, log odds can be conveniently translated into probabilities, as we've seen in the logistic regression examples, using the sigmoid function. So 1 over 1 plus e to the power negative log odds would give us the probabilities. So this probability that we have computed is our baseline prediction. Now we will have to update this in this table like this. For all the cases, right now, the baseline prediction is 0.6. To understand this better, like logistic regression, you can imagine the scenario is like this. So we have 2 points predicted as zeros in the status column, and we have 3 points predicted as ones. This is what we are shown. This value of sigmoid we know is always between 0 and 1. And this 0.6 here represents the line, which is our prediction. So you can see that right now, we are not accurately predicting. For these points, there is a difference. There is an error. And that error is also called residual. So this line, had it been at 1, we would have predicted these accurately. But there is a difference. On the other hand, here too, we have an error. This line is not exactly mapping the level of 0. So it's an error again. Now we want to progress in such a way that we are able to minimize this error. But first, let's begin by computing the difference between the actual label and the baseline. So this actual label minus the baseline is the value that we get here, which is known as the residual. These are the errors. For these 3 points, you can imagine the error is 0.4. For these 2 points, you can imagine the error is negative 0.6, actual minus the prediction. Now, gradient boosting would begin making predictions by using a simple model, which could be a decision tree or any other simple model. So let's say we came up with this kind of a decision tree, which is a very simple decision tree, which says that at the root level, we are checking whether the credit score is less than 750 or greater than or equal to 750. If it is found to be less than 750, then we check the work experience. Is the work experience less than 4 or greater than or equal to 4? And following this path, we can map the values of the residuals here. This is the major difference. These trees are not going to predict the actual value. These trees are going to focus on minimizing the error. That's why we call it gradient boosting. The gradient is applied to the loss. We want to minimize the loss to an extent that we are approaching accuracy. In all of the models that you've seen, we've always been making predictions on the labels that are given to us. But gradient boosting focuses on the residuals or errors and tries to minimize them. So let's see, how do we map these residuals on the tree? First, let's look at this node. It is pointing towards those observations which have the credit score greater than or equal to 750. If you see in our data, we have only 2 such observations. And what is the residual corresponding to those? So both these observations will be mapped to this node. Likewise, if we come to the scenario where we have less than 750 credit score, which means we are referring to observations 1, 2, and 5. Then out of these observations, 1, 2, and 5, which all observations have the experience less than 4 years? Only this observation. And this will be mapped to negative 0.6. What about these 2 observations? These 2 observations would come to the right, and they would have the residuals as 0.4 and negative 0.6. So we can write it like this. We've just mapped these residuals as per the tree model that we are trying to the nodes. But this is not the value that the node is giving. How do we actually derive the value or the output of the node? There's a formula for that. The formula is we do a sum of residuals for that node divided by the previous probability multiplied by 1 minus the previous probability. And if you have more than one observation at a place, you'll have to add this term too. Let's take an example to understand how this works. Let's concentrate on these two rows, which have this output 0.4, 0.4, which is here. Now, if we put these values here, doing a sum of residuals, it will be 0.4 plus 0.4 divided by what is the previous probability? This is nothing but the baseline probability right now. So we will do a 0.6 multiplied by 1 minus 0.6 plus the same expression. If you solve this, you'll get a value which is 1.67. What is this value? This is actually called the node output. Now, following these steps that we did for these two observations, we can find out this node output for all the observations. And it comes out to be something like this. So we got the node output, but eventually we would want to get an updated value of the log odds ratio. Initially, we got the baseline probability using the log odds ratio. So how do we update the log odds ratio and then in turn the probabilities? There is a relationship between this node output and the updated value of the log odds ratio. And that looks like this. So updated log odds ratio would be the old log odds ratio plus the learning rate, which is a hyperparameter, multiplied by the node output. How do we choose this learning rate? Now, this is a trade-off. We'll have to experiment with these values. If it's a pretty high learning rate, it is quite likely that we may not get the best result. And if it's pretty low learning rate, it may take a lot of time. We'll discuss more on this when we do the hands-on aspect. But as of now, let's just say this is some hyperparameter which is controlled by the person conducting the experiment or working on the model. Let's say we take these two records now and see how the log odds ratio will be updated. So we can see we're using the old log odds ratio, log of 3 by 2. We calculated it. Plus, let's say we've taken the learning rate as 0.1 and we can choose other values as well, which we'll discuss, multiplied by the value of the node output, which in case of these two records is negative 0.42. So for each record here, which have the node output as negative 0.42, the updated log odds ratio is this. Let's add this to the data, and using the same logic and the node output and the learning rate, we can find out the updated log odds values for all the observations. Once we have the log odds ratios available for all the observations, we can easily translate that into probabilities using the same sigmoid function. So if you see, what is happening is you started with a baseline, calculated the residuals, then you applied a tree which tried to minimize the residuals. Based on the output of the tree, we are once again calculating a log odds ratio and updating the probabilities. So these updated probabilities would lead to new predictions, and those new predictions should get better with time. Let's see. So updated predictions lead to updated residuals. So these updated residuals would now be targeted for reduction by the new models. We will use multiple trees or multiple simple models to keep on targeting the residuals for minimization. That's the approach that gradient boosting takes. Now you can imagine finally, you'd be seeing something like this. Let's say you have a sequence of trees, one after the other. Trees could vary in design and size and architecture, but these are multiple trees that we have tried. And our final prediction here would be the old log odds value where we started with, plus the learning rate times whatever is the final prediction from each tree. This T1 represents the first tree, T2 represents the second tree, and so on and so forth. So we generate a final prediction. And since at each stage we have been targeting minimization of the error or the residual, eventually we achieve improvement over the iterations. So this is how gradient boosting works. Like I said, we'll discuss some of these portions related to the hyperparameters when we do the hands-on piece. Hope you had something new to learn from this video.